then. Thank you for the opportunity for letting me share my research on the homogenization of land surface air temperatures using 20CR reanalysis. Next slide, there we are. As you're well aware, there are several global estimates produced by independent organizations, and they all have agreed substantially in the trend and the fact that the globe has warmed since the industrial period. But when you actually examine each individual data set, you find that they are not as independent as you may have first expected. Most of them use some form of neighbor-based assessment for homogenization, and most, if not some, or some, if not a lot of them, borrow the same data set from others or use the exact same data set. All of them have the same problem in cases of sparse sparse observations, whether that's in time or in space. Using 20th century reanalysis has the opportunity to fill that gap and produce a new set of estimates. The advantage with sparse input reanalysis products, such as 20th century, is that it is fully independent of the observations and it's constrained and only assimilates the surface pressure observations and not temperature. The first 20th century reanalysis product was 20CR and followed by 20CR2C. Europeans produced the RA 100, and recently then the coupled reanalysis circa 20. The work that we did is following on from the work of Leo Hamburger, who successfully homogenized radiosonde records using full input reanalysis. And the question of my thesis was that if can 20CR reanalysis perform a similar function? Prior to doing the homogenization, several bits of work were required as precursors in terms of determining how good the reanalysis product was compared to neighbor-based approach. Earlier products like 20CR2C had some difficulties, and while it corresponded very well with surface temperature observations, there was periods and times and places where it had challenges. Now, to decide on which product was best, if any, of the reanalysis products, we looked at 20CR2C, 20CR-V2, which only came available halfway through the research, ER20C, and as I said later on, in the coupled reanalysis circa 20C. Check that using the standard deviation of the different series and compared to the neighbor-based approach, and also the correlations of 20CR to stations versus the neighbor-based approach. And we found that in where observations were plentiful in time and in space, that pairwise homogenization remained the best method for homogenization. However, if the medium neighbor of a group of competitors was greater than 700 kilometer distance from this test station, the advantage changed to the 20C reanalysis product. And between 300 kilometers and 700 kilometers, they were compatible. Now, this map just shows the significance of this, because the area of the world where pairwise homogenization, where it was developed even, and where it is the best, is in the yellow-brown section, which is the smallest part of the globe, as you well know. The blue section is the stations, or the blue marks are the stations between 370 and 700 kilometers distance, where sparse reanalysis products showed to be equivalent or as good as pairwise homogenization. The red stations are the stations where pairwise homogenization was not as good as reanalysis in terms of a competitor series for homogenization. While the numbers are smaller, less than 1,000, the area of the globe and the significance of them in the land-based area, given the fact that the amount of stations in a grid determines the temperature of that grid, which feeds into the global trend, becomes quite significant. So, having decided that 20CR-V3 was perhaps the best sparse input reanalysis product going forward, initial homogenization attempts were made. Before doing that, obviously quality control had to be applied, and in this case, it was felt that a robust method of quality control was 3 times the interquartile limit, or range, I should say. So, using the standard normal homogenizing test, which is a similar test used in GHCMD4, which I have used as a benchmark, if you like, or as a competitor, direct competitor, because of its availability and the commonality in the data set. That the standard normal homogenizing test applied in this time with a 10-year moving window, 5 years each side of the break. If a break had a cessation of greater than 36 months, it was set to missing. This approach produced 4 different estimates based on the work of and following the work of Hamburger et al. 20CR-V3 long, which was full segment, which meant that the adjustment was based on the mean of the series before and after the break, and 23CR-V3 short, which restricted the differences to 5 years each side of the break. Now, using also rich procedures from Hamburger et al., looked at neighbor segment approach. In this case, I selected 250 nearest neighbors to find an adjustment, and if assuming 1 or more, the median of that number of those ones was selected as the adjustment. Another neighbor-based approach was the double difference approach, which is similar to used in many of the numerical weather forecast predictions models, which was basically neighbor segment, which was the difference between the neighbor 20CR and the difference between the differences of the station minus 20CR estimates. Now, having carried out the homogenizing test, this station is a long-running, centennial-long station at the Bult in the Netherlands in a well-sampled area. And 3 breaks were detected in this instance. You can see that the earlier period, the variations or the variance is completely different than the rest of it. And this is a result of moving the Bult station from one location to another in the early period. No standard normal homogenizing test will detect a break with variance, but only in the mean, unfortunately. The breaks are visually compatible or agreeable with the what the algorithm detected, and look reasonably good. When we used a neighbor-based approach in this analysis, the approach taken was to fall back on a 20CR-V3 short estimate if a neighbor estimate for a particular break in time could not be determined. Most analysis would, other than this analysis, would have to leave that as missing. I just put in this map just to show the about the times that one station had one break that deferred, or one or more breaks that deferred to 20 CRV3. And there's 4 maps there. The legends are a little bit difficult in this one. I don't know why they're so bad, but the one I want to bring your attention to is the one in the left right-hand corner, the blue one, which is post-1950, which is very interesting because the large amount of times that in North America, particularly, that a deferral to 20 CRV3 was made. And it appears to be associated with the changeover from, particularly from the changeover from liquid and glass maximum minimum thermometers to transistors, I should say. Overall, the distribution of the adjustments looks like this, with the outlier being the neighbor segment with no missing middle, a feature in most homogenizing processes, and particularly also seen in GHCM before. By construction, they all have the same number of breaks. The mean values are slightly negative, minus 0.1 plus a bit, and very compatible to, as I said, to GHCM before. Returning to the bolts after post-homogenization, the final segment was adjusted so that all time series overlap and are exactly the same. The benefit of this was to highlight the differences in the methods. And as can be seen in this particular station, as I said, which is in a well-sampled region, they are very, very close, right back to the 1850. The red one between 1850 and approximately 1900, obviously, is the raw data. So everything has adjusted prior to 1900 to be a lot cooler than the raw data. But if we look at a sparse input and reanalysis region, and I picked this one particularly because of the number of breaks involved, you can see there's quite a bit of variation involved. GHCM seems to mirror the raw data quite significantly and quite closely, suggesting either that they used a completely different way of homogenization or that they were unable to homogenize the breaks because of the lack of sufficient or suitable neighbors. Overall, on the assessment on the station series basis, we looked at several hundreds in actual fact, into the thousands individual sites, and it did show a marked difference. For different stations, it can be seen that some different methods are outliers, but on occasions, or quite often actually, GHCM itself was an outlier. But no overall pattern can be ruled out as any of the approaches as invalid and or unreasonable in their approach. If we turn to gridding, and in this occasion, I've only put up one slide, and this is 1900 to 2014. On a global scale, overall, all series, all adjustments are reasonable. There is things to note, though. If we take GHCM v4 as the benchmark, if I can use that word, although it's not correct, or it's the standard, there is a somewhat difference, particularly over the Indian subcontinent, where our 4 new approaches have shown cooling, whereas GHCM v4 is showing warming. Ditto for parts of North America, but predominantly the difference seems to be the Indian subcontinent. So on a monthly anomaly basis, and we're not shown, there are differences relative to the month-to-month, but they can be seen. British trends show difference principally in the earlier periods, 1850 to 2014, but they tend to merge and agree much more in the latter period, particularly from 1950 onwards. And the sparse regions show some difference, but not much in the latter period. But overall, there is nothing in the analysis that would indicate that this method is unreasonable. If I take the 5 main or 4 main data sets, Berkeley, Crutum, GHCM, and we've also included Chinese latter land surface data sets here, and overlap the established data sets, if I can call them that, are broken lines, whereas my estimates are solid lines. You can see that over the period, they are a very, very close correspondence. In the latter period, the established data sets seem to show slightly more warming than the 4 estimates produced here. And there is some differences pre-1900s. Trends by OLS trends per decade from 1850 to 2014, and I've chosen 4 periods, and you can see in the last column the changes between the 1950 period and 2005. What can be seen very easily here is that post 1980 to 2014, obviously as observations, etc., are much improved, but there is close correspondence. In fact, they're almost identical. Post 1950, there is very good correspondence between all of the 4 estimates and the 20C or B3 estimation method. What is interesting is there is a divergence in the earlier period, 1850 to 2014. But what is interesting, the 1900 to 2014, is the close agreement between the 4U estimate and the Chinese estimate in particular. Whereas the other ones diverge, but Chinese estimate is very, very close to 4 estimates that we have used in this analysis. So the global behavior, all series broadly agree on an interannual and annual basis. The new estimates do show less warming from the early period, mainly arising from the pre-1900s, possibly associated with the lack of observations at the time, or it could be a bias that is in the 20CR analysis that is manifests itself in this way. Bear in mind, as I say, that perhaps with the exception of Berkeley, that chose a completely different method in terms of homogenization to the other methods, the pairwise analysis had a lot of similarity in terms of how they produced their estimates. But depending on the comparison and depending on what you're comparing, the differences could be up to 40%. Now, this is only an exploratory analysis, and it is not a operational or suggested to be an operational analysis. The first thing, it is a one-run estimate only without an ensemble. I have looked at some of the main systematic procedures that were used in the analysis for part of just looking at the possibility of an ensemble, but time limits prevented an ensemble to be used. If in the early analysis, critical value for the standard normal homogeneity taste based on all the analysis carried out and reference to literature suggested best that the critical value should be between 12 and 18. I chose 16 as a reasonable estimate. It produced 55,000 or 53,000 breaks in the entire series against GHCM that ultimately produced 72. If I changed that and reran it again, which I did, using a critical value of 12, I also produced about 73,000 breaks, which was very compatible to GHCMB4. And in that case, the differences between GHCM4 before and my estimates would have improved by over 15%. So further analysis is required as to what is going on in several parts of the world, and these tend to be sparsely sampled regions. Particularly India is a case of note, as we spoke about, and of some interest. Unfortunately, the downside of sparse input reanalysis products? Well, firstly, the European versions only go back to 1900, so that limits their utility in terms of the earlier records. But going forwards, they terminate in 2014, which means that the harmonization using sparse input reanalysis in the latter period for the sparsely observed areas is limited in some way, would have to be got around that. Possibly that 20 CR and not follow-on sparse could be informed homogenized assessment of temperature and other surface pressure parameters is certainly a possibility. It'd be interesting to see, as a case in note, by the way, the results of the circa coupled reanalysis in my analysis did not perform as good as ERA20C, which was interesting, and I can only assume that it's something to do with the coupling, and that because it performed so less advantageously, it wasn't considered for further options. But Reanalyses 20CR sparse reanalysis is improving with each iteration, and all of them are shown, and it is showing possibilities that there is a possibility to move forward for harmonization in the sparsely sampled areas and epochs using reanalysis products going forward. And that is the total summary, very short, of the thesis. Thank you.
Brilliant. Thank you very much, Ian. That was great. Thanks very much for presenting that to us.